Our next speaker is Dr. Hossein Mokhtarzadeh. He got his PhD from this university a few years ago in knee injury and has gone on to work with the Harvard Medical School, where he's developing 3D models to predict spinal fractures. He also supervises students at the university here who are developing new 3D printing applications.
Thank you very much, and thanks for inviting me to give this talk. First, I'll talk slightly about 3D printing, but then I'll move on to basically what will nicely set the scene for me, talking about spine. So I'm going to talk a little bit about spine and what's happening there and how we can predict spinal fracture using biomechanical or mathematical models, for instance. So this semester I was so lucky to be involved in this Biomaterials course with Professor Peter Lee from Biomedical Engineering. That was an amazing experience, not only for me, of course for the students as well. They had no clue day one about 3D printing, about 3D modeling, CAD, pretty much nothing. Some of them may have, but basically most of them they had no clue. But at the end, they come up with a design, they come up with a problem, and then they try to solve it in a group of 2 or 3, and we were really impressed. Now they're actually giving their talks and their presentation. This is part of what they have done. I don't go through the details, but you can see they actually defined the problem and then went and tried to basically dig the literature and come up with a solution, and we help them through that. We teach them like how to do it in Mimics. We have some people from Mimics here or Materialize. And then SolidWorks, and even I just taught them just one session on finite elements, which means that we want to know what the forces are in the body. But they most of, we didn't expect them to do it, but they did it, and they come up with some solution. It was really amazing. That was amazing. So this is another one. I don't know if Luke is around here, so it's not right, but he was supposed to be here. So he actually, the team did for the hip. So this was the cup and taper reorientation of the novel reverse hip, basically hip processes, and they tried to come up with a new solution, and they went through all the steps and to print it as well. So if you want to know more about this, I'm happy to talk about it after this. Well, what I'm going to focus today is this one, and a particular part of this flowchart. So in whole orthopedic, if you look at what, for instance, I'm not a surgeon, I'm an engineer, so excuse me if I just say something that may seem quite silly from this, what do we call surgeon's point of view. But if you look at what's happening in the theater, for instance, or if you want to develop some sort of 3D printed material, so you go from the imaging, and then there would be patient-specific modeling, and the surgeons would develop some ideas or planning. But then the engineers would come. Of course, engineers are involved in the top part as well. But here, mainly these days, engineers can help in terms of what type of loading. For instance, you want to design something for spine or for hip. But is this gonna withstand the type of loading that person basically sees during or feels during daily activities? So how can we do that? How can we optimize that? Can we just print it and put it there? There's a lot actually going there, and people are focusing on that. So you see that where engineers coming and playing a major role. I don't think this is just one way. I believe this is like iterative. So nowadays, so I was so lucky to be sitting in a lab which was Harvard and MIT's lab basically, and we had like people from MIT, people from Harvard, and they were working so closely. And that was amazing in the sense that even PhD students from MIT, they were going through all the Harvard's basically labs, Harvard Medical School's lab, and they're trying to learn more about the medical applications of what they were doing. That was really amazing. I guess there's something happening in Australia, but I'm happy to talk more about this one. So what I'm going to focus is this part, basically this part of the this flowchart, which is the finite element part of it and the loading that go through every single joint, for instance. This project, I don't know, have you heard of the Framingham heart studies? Raise your hands or I'll tell you. Okay, perfect. So for those of you who don't know, again, it was a privilege to be part of this. It started in 1948. They first started for heart disease. So they wanted to figure out why people actually die because of the cardiovascular issues. They started to grow up people. I think originally it was like 5,000 people, and they followed them up to now. And it's just keep going. And so we were dealing with longitudinal data for more than like 3,000 people. I did my PhD on like 16 people, and when I went there, it was like 1,000 people, just like simulating, and I was like, oh my God, what's happening here? So this is really amazing to go. And I guess there are some studies in Australia happening. There's Geelong study and some others. I would be happy to talk to you about if you have information about those kind of studies. So when my supervisor came from Stanford to Harvard, she actually saw this QCT data, and she said that, look, we see a spine. So since then, about more than 20 years ago until now, she's been getting NIH grants, and she's been developing the osteoporotic part of the Framingham study. And this is a huge program now. So as I said, we have data for more than 3,000 people, and we have their spine curvature, like we have the QCT as well as the CT, normal CT. So spine curvature can be found, as well as because you have the QCT, so you can get the muscle morphology as well. So we can have a patient-specific models as we go. So one special application of the models that we develop is vertebral. We want to focus on, our lab is focusing on the vertebral fracture as well as very much all the bone fracture or hip or a spinal fracture, but my focus was just a spine fracture. So vertebral fracture is common, especially when we age, especially among women more than men. So it's a huge issue, because when you have one vertebral fracture, it will lead to another one and another one, and then it will even increase the risk of hip fracture, which is really very challenging, because it will be up to that after hip fracture, the likelihood of what do we call it? Even we have like 20% increase of mortality after 1 year or so, if I'm not wrong. So you see that how close they are in terms of one injury, some like spine level, and then leading to other types of injuries or fractures. But the question is how vertebral fracture occurs. We have a spinal loading, right? As you can see, we have vertebral basically loading, and in the meantime, we have vertebral strength. So if you have strong vertebra and the loading is not exceeding that, so you're fine, right? So you have to consider both, basically. And in terms of understanding them, we have quite a lot of information about vertebral strengths because of imaging. So you can get imaging, and then you get basically even non-invasively, you can get the strengths of that material or vertebra. But in terms of vertebral loading, what do we know? Can we put just something inside? It's not very easy, right? It's very invasive. So this is the part that we actually try to understand and figure out while you're sitting here. What's the load going through your joints? If you just walk, what's the load going through? Any type of activity, and if you develop something like a 3D printing or any other material you want to put in the body, then we first should know all these basically the issues related, because it may lead to fracture, it may lead to other types of, let's say, just biomechanical or other types of issues. So as I said, people have done, I didn't tell you about it, but people have done, predicted or measured spinal loading, or even hip loading, other joints as well. So they put sensors there and they actually measure that. Or they even put sensors inside the, what do we call it, the disc itself. So they measure the pressure, which is an indication of the force that goes there. But as I said, it's a challenging one. Yeah, you would not allow us to do this, right? So you want us to really predict it. That's where we are. So this is epidemiological data that shows where the fracture happens for the osteoporotic patient. So you can see there's a major peak at the thoracolumbar, what do we call it, regime, right? There's another peak in the mid-thoracic one that some people don't believe in it. They say that's just because of the data, but at least everyone agrees on the thoracolumbar. So our point is, can we predict this? So how can we do that? How can we predict? Because if you want to predict this one, it will help a lot. Like if you want to design something for the spine, so this loading would help you, right? So you can actually design it based on the loading that you got from here. So this is the whole procedure that we do. We get the data from Framingham Heart Study, QCT. We actually get this, the bone, the muscle morphology. We actually measure them and put them into our model. And in the meantime, we have the curvature. So every single person has their own curvature, right? So we actually take into account that curvature. We put them all together into a mathematical model. We call it biomechanical model. And this is a unique model that we developed in our lab. It has got more than 500 muscle fascicles. We've got the rib cage. We've got basically thorax, a lumbar, and I recently added the cervical part. So we are completing this one and we're adding the lower limb to it. There will be a full body eventually. So you remember I talked about like loading. So this is the way we want to figure out what factor of risk is. What is the risk basically involved in different activities? So we put this person from Framingham heart study into different types of activities. Then we get the loading, every single level. In the meantime, we work with a company that actually developed in our lab, and now it's Berkeley. So we get from QCT data, we get the vertebral strength. So we have vertebral strength, we have vertebral loading, divided, so it would be the factor of risk. So you see the risk of that person if the fracture would happen or not. And that would be an indication of that. We remember that curve, where the thoracolumbar junction had the peak of the risk, right? Where the fractures occurs. So this was our question as well. So when we put them all together, all these activities, we see the same pattern. So that's actually exciting. It shows that our model can predict this epidemiological data. And now we can come back because what we have is we know what the muscles are doing. What's the loading going through every single muscle fascicle, and what's the load going every single joint level. So now it can be used for training purposes, for predicting, for pretty much, or even like 3D printing, for instance. If so I'm working with a company dealing with the spine again, what they want to know, how they can optimize this, but they have no clue about the load. So they want us to predict that load for every single person. And you have to have data for that person. All right, and this is going to be really helpful so our new NIH-funded grant for the next 5 years will be to develop this model for every single person. And we are trying to minimize, because this is now taking time. Because we have data, we have to do the muscle morphology, curvature, it takes quite some time. But in the next 5 or 6 years, we will actually expand upon that. They will be much faster to develop this model. So eventually, this is the whole idea. Biomechanical model and imaging. This is the imaging technique that is being used now in clinics to predict bone fracture, which is it takes 10 minutes, you go there, but here you have no data in terms of like loading. You just have data for instance, a kind of surrogate of the strength, because it's not even 3D with this DEXA machine. Or we can have the QCT data, but it's quite expensive, I guess, or other types of imaging, right? So we're trying to combine them all. So imagine this is the only thing that happens in clinics. So we're trying to bring this into clinics as well.